All right, let's resume. Okay, so far we have done numerical analysis. Okay, so I hope that we kicked it all the way. And we also, so far, you guys have been rocking Python. So if this was Python and that was you guys, you're beating the crap out of Python. So love it. And next, we're going to attack algebraic equations. Okay? So this is the first unit of the class, and this is really where we start getting into more applications and more useful stuff. So the first chapter was just a warm-up. These are errors. This is how we do some coding. It's going to get more real now and more useful. In this first unit, we will focus on two things that all fall under the umbrella of solving algebraic equations. So you will learn tools to solve algebraic equations. Algebraic equations are simply equations that don't have derivatives or integrals in them. What that means, they're either linear equations like 2x plus 3y equals 0 and 7x plus 2y equal 1, or nonlinear equations, cosine u equals 0.1, solve for u, or a system of nonlinear equations like the one below, x cubed plus y equals 4x, and y equals sine x, e to the minus x, find x and y. So in the next few weeks, we will be focusing on tools to solve equations that look like this. You obviously know how to solve a linear equation with a single unknown, 2x equals 3, x equals 3 over 2, right? Or a small system of equations, like 2 or 3 equations, a few unknowns. Maybe a little bit more. Gaussian elimination. Has anybody done Gaussian elimination? Okay. So you're familiar with some of those, at least on the linear side. You might not be too familiar with the nonlinear equations. So we will cover all of that. We'll teach you the tools, and they're going to be really, really, really important for next year for you. Our first part of Unit 1 is linear solvers, and I'm going to start with a motivating example. Okay?
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in the injury of 7 Prince George's County firefighters. On February 24th, 2012,
Can you hear?
a wind-driven fire in a condemned single-family residential structure resulted in the serious injury of an officer and forcible entry firefighter from Truck 809 of the Prince George's County Fire Emergency Medical Services Department. NIST examined the fire dynamics of this incident at the request of the department. At 9:11 in the evening, a call was dispatched for a residential structure fire in Riverdale Heights, Maryland. Truck 809 was the first due truck and arrived on the scene within 3 minutes of the dispatch. The 809 officer observed smoke moving extremely fast through the front yard and across the street. The Truck 809 officer and forcible entry firefighter proceeded directly from the truck to the front door of the structure. Less than 1 minute after the arrival of Truck 809, officer and forcible entry firefighter, both in full PPE and SCBA, have entered the structure and began their primary search of the first floor. Smoke and heat conditions on the first floor worsened, and the front door slammed shut, trapping the 2 members of Truck 809. Within 30 seconds of the door closing, the Truck 809 officer cleared a portion of the living room window on the front of the structure and exited to the outside. Truck 809 forcible entry was unable to self-evacuate and continued to endure the elevated thermal conditions in the living room. Although Truck 809 officer had sustained injuries and damage to his SCBA, he alerted other firefighters that his crew member was still inside. Fire attack had started from the basement door on the rear of the structure. The front door was reopened, and a group of firefighters, including the Truck 809 officer, entered the living room, found the downed firefighter, and pulled him outside through the front door.
In February of 2012, I had a fire on 57th Avenue in the Riverdale Heights community. It's a single-family house, just like any other small single-family home in the county. First responding units reported smoke and fire showing from a basement level. It's about 9 p.m. It was a red flag day, meaning the Weather Service had instituted a red flag warning for high winds and dry conditions. The truck and the engine arrived together. Truck crew of 2 for the inside crew went ahead of the engine line. They were going to initiate a search, what appeared to be an occupied home. They made it in a front door that had a swing opposite what you would consider. So instead of swinging to a wall, the swing was into the middle of a room. Fire was in the basement below. When they entered, the hose line had not made it in the door, and the energy from the flow path that was now created coming up from the basement steps and now out the front door that they had just opened, that energy slammed that front door shut behind them. Within a matter of 2 minutes, those first 2 firefighters became trapped, and one of them incapacitated. The one smaller of the 2 was able to bust out one window, which was not big enough for him. Of course, that created another flow path. He got to a bigger window, bust that out, created a bigger flow path, but he was able to get out. He was then able to get the engine crew, who was still on the front porch, had not made entry yet. He was able to get them to help him force open the front door and pull the other young man out. That young man was in a burn center for 45 days, nearly lost his life.
NIST's Fire Dynamics Simulator, or FDS, was used to provide insight into the dynamics of this structure fire. The results of an FDS simulation are visualized with another NIST program called SmokeView. The inputs and details for the FDS simulations are documented in NIST Technical Note 1870. The fire started in the basement near the windows on the rear of the structure. Based on an assessment of the fuel load in the burned area of the basement, the estimated peak heat release rate of the furnishings and interior finish was approximately 9 megawatts. However, the lack of oxygen limited the fire growth until the front door was opened. As seen in the heat release rate graph, after the door was opened and allowed additional oxygen to enter and mix with hot fuel gases in the basement, the fire heat release rate increased, with some of the burning occurring on the first floor. Comparison of the simulated initial fire conditions in FDS versus the post-fire damage of the exterior of the basement corner, where the fire started. The wind was blowing from the rear of the house to the front. In the model, a steady wind speed of 20 miles per hour was used. The output from the FDS simulation can be used to provide insight to the flow path within the 2-level structure. Fire gases move from regions of higher pressure to regions of lower pressure. Notice on the outside of the structure that the upwind side of the house, or the rear of the house, is under a higher pressure than the downwind side, or the front of the house.
So green is higher than the
The
blue.
inside of the house has been pressurized by the wind from the openings on the rear side and the pressure from the fire gases. Once the front door is open, the high pressure on the rear of the outside of the house and the inside of the house equalize. One of the hazards to firefighters located in the exhaust portion of the flow path is convective heat transfer from the fire gases. Convective heat transfer depends on the velocity, the amount of turbulence, and the temperature of the fire gases.
So there's it coming from the
This
top,
video
that's the
shows
rear.
the change in
Then
gas
they open the
flows
door,
from the first
comes out the basement,
door was opened.
creates a flow path, brings the heat.
Gases from the doorway at the top of the basement stairs to the front door.
Yeah.
An arrow shows how the hot gases traveling at 10 to 20 miles per hour would have impacted the front door and forced it closed behind the Truck 809 crew. This video shows the calculated change in gas temperatures as a result of opening the front door, which increased the flow and mixing of the fire gases within the house.
Brought the temperature higher, look at the red, so 800 degrees.
Wind can generate hazardous thermal conditions within a flow path. Stay upwind of the fire or keep the wind at your back. Uncoordinated ventilation or uncontrolled doors can also be the cause of increased thermal hazards within a flow path.
Oh, look at the fire in the back.
When sizing up a structure fire, choose your tactics with potential flow paths in mind. Recall that in a flow path, the hot gases move from a region of higher pressure to a region of low.
Okay, so that drives the point. What is the, I don't want to scare you with these things, but the point here is that this technique, actually one of my friends and colleagues develops this fire dynamics simulator code. We've contributed to it as well for fire simulation. But the technique used is called computational fluid dynamics, and it solves for air, gas velocity, temperature, and pressure. And the trick is you take a problem like this and split it into small chunks, and on each chunk, you develop an equation. And the totality of those equations become a system of linear or nonlinear equations, which is exactly what we will be studying here. We will solve a heat transfer problem and come up with 1,000 or 10,000 or 100,000 equations to study how the temperature varies, okay, in a plate or in a rod, subject to different temperature conditions, okay? So that's the point of this example, is to tell you these realistic problems that do guidelines for firefighters, they're based on what you're learning in this unit. So hope you pay attention. All right, thank you. Off you go.